Hi guys, this is Sakshi and I welcome you all to my tech platform, Way to Learn. So before we go into the video, like my videos, share my videos, subscribe my channel and do not forget to hit the bell. So let us go into the video which is from quantum mechanics in part 9. In my last video, we had been doing some important points on wave function and the formulas regarding the wave function. So here now we are going to learn about the Schrodinger wave equation. So why is this Schrodinger wave equation so much important? So first let us just think about a story kind of thing. Okay, now we have a system and that system on solving the boundary conditions and so on, it has some constraints and everything. The system has a particle and that system comes reduced. Okay, that system which has a particle in it and with some boundary conditions, some constraints, it gets reduced to a equation, and that equation is the Schrodinger wave equation. Now we get the information on particles only when we have a wave function. So that Schrodinger wave equation has the wave function in it. So on solving that wave equation, we can get our wave function. So that wave function has lots of information on the particle, and that wave function when operated by an operator will give us a lot of information. So we have a wave equation which is Schrodinger wave equation which contains the wave function. So on solving the Schrodinger wave equation, we get the wave function which has lots of information about the particle, and we have an operator later on which operates on that wave function, and we collect the information about the particle. So this is the basic thing. So let us see the Schrodinger wave equation which is time independent and time dependent. So we know that our position, that is our wave function, depends on the position and the time. But sometimes it does not depend on time, it will depend only on the position, and hence the wave equation is categorized into two, time independent and time dependent. So for time independent, we have to learn this. This is the basic equation used everywhere, which is h psi is equal to E psi. On solving these within operators, we will get our wave equation. So h psi will be equal to E psi is the common equation used. So h over here is an operator and E over here is the eigenvalue. H is equal to p square by 2m plus v of x, which is potential, and for time dependent, again the same equation, h psi is equal to E psi, but over here h is an operator and E is also an operator. So h is equal to p square by 2m plus v of x, and E will be I h cross dou by dou t. This is a special case for time dependent function. So now let us just get the wave equation and then we get the solution. We will find the solution and we will get the wave function. And we'll also get some important points through that. So let me consider the particle is moving in one dimension in a potential v of x, and the potential is v of x, and the wave function psi of x is associated with the particle. So the wave function which is associated with particle is psi of x. So this is the basic equation, h psi is equal to E psi. Now we know that h is equal to p square by 2m plus v of x. And here I am considering this as time dependent. So E is also an operator. So I have operated that E over here, I h cross dou by dou t. And I have also used the momentum operator instead of p square. So you can see I have used minus I h cross dou by dou x twice because it's p square. And this is in one dimension, so it is in x. So this is the basic equation. So next, on solving that, we get this. On solving the before equation, we get this, and this equation is called as time dependent Schrodinger equation. An important point to know, you can but easily know, just remember E psi is equal to h psi and remember the operators, and you just have to substitute on your own and you'll get this equation. You don't have to remember this huge equation every time. You can just use h psi is equal to E psi, substitute the operators, and you'll get this time dependent Schrodinger equation. Now we can solve, okay, you'll think about the time independent. We'll also get the time independent Schrodinger equation as we go on. But before, now we have an equation over here. So we'll have to find the solution for this equation. So we can solve the above equation using the separation of variable method. Okay. So now I'm going to use the separation of variable method over here. Again, if you do not know how to solve a differential equation, please go to my differential equations from mathematics playlist. You can find all the methods to solve a differential equation. So that will be helpful for you. So you can just check that on too. So we can solve this above equation using the separation of variable where there are two variables over here. One is the position and other one is the time. So psi of x comma t will be equal to psi of x into t of t. Okay, I have removed these two variables. Okay, x as one part and time as other part. So I'm not going to solve this entirely. What we do is we multiply and divide the like we have to substitute this psi of x comma t as psi of x and t of t. We just have to replace that, and after that we just multiply and divide by the same psi of x comma t. So on multiplying dividing you get this simplified equation, and after simplifying that we have like one is LHS and other one is RHS, and we have to equate the LHS and RHS to a constant. Okay, so this is the basic steps for separation of variable. Now you can for detailed method you can check the differential equation video. So now on solving this we get this particular equation below here, minus 1 by psi of x h cut square by 2m dou square psi by dou x square plus v of x. This is an one part LHS, and the RHS will be equal to I h cross by t dou t by dou t, and this is an RHS. So I have LHS and RHS. Now this next step will be to equate it and constant. So I'm equating it with a constant over here, which is equal to E. And I'm going to equate these two LHS and RHS to be the same constant. So this is a simple thing I'm going to do. I'm going to just equate these two with the same constant E. So now we have space part and time part. Now for space part, I am going to consider the space part to be psi of x because I have separated my variable, that is my LHS as LHS. I am just solving the LHS over here, and the time part will be my RHS. So I am going to solve this space part over here. So I have the LHS minus IH cross h square by 2m dou square psi by dou x square plus v, which is equal to the constant E. So now I am just simplifying it further, and I get this the one which is in the square. So if you see, I get h psi is equal to e psi, and e here is a constant which is an eigenvalue. So when we solve the space part of time dependent Schrodinger equation, we obtain the time independent Schrodinger equation. So this is the time independent Schrodinger equation. It is nothing but you are just going to substitute for h. But this is also obtained by solving the space part of time dependent Schrodinger equation. So an important thing to know. And then let us see the time part. So on time part, on solving the time part, it is a few steps. You can just solve that. On solving time part, I get a e power minus I e t by h cut. So this is my time part. Now, if you remember the solution should be psi of x comma t is equal to psi of x and t of t. That is, I have to substitute my psi of x value and t of t value. So I'm just going to substitute my psi of x as it is, and my t of t will be e power minus I e t by h cut. Okay, so now your wave function for time dependent Schrodinger equation is given as psi of x comma t is equal to psi of x e power minus I e t by h cross. So this is an important relation that you have to remember, okay, because this is going to help us further. So now this is the further. So let's psi 1 be psi 1 of x e power minus I e1 t by h cross. So now I'm going to just superimpose the wave functions. So the first wave function is this and second wave function is this. So basically we superimpose this wave function and write the main wave function. These are the sub wave functions, right? We are going to write the main wave function. So psi will be equal to C1 psi1 plus C2 psi2. Okay. So now I can also replace this with my solution C1 psi1 e power minus I E1 t by h cross plus C2 psi2 e power minus I E2 t by h cross. Now, this particular thing is called as time evolution of the wave function. So, you will learn that when we do it further, when we go and find the time, like we can do this in the problem. We can do this thing in the problem when we solve the particular problem where time evolution is used. We have many problems from gate and net as well. So we'll be solving gate problems, net problems, jam problems, TIFR problems, JEST problems. So we'll be solving all the 5 problems, like 5 exams problems. So we'll have so many time evaluation problems. So you'll learn that from them. Now let us see the stationary states of Schrodinger equation, which can be obtained from the time dependent Schrodinger equation. So now we have the time dependent Schrodinger equation solution. So we are using that again psi and psi star. We have found psi and psi star. So in the psi star, r minus I will be replaced by plus I. And now after finding the probability, you get psi star into psi because our exponential terms get cancelled because one has minus I part and the other has a positive part. So it will be e power 0. So the probability will be equal to psi star of psi. Now I can say directly from this that the probability is independent of time for a stationary state. So you can easily remember that the probability is independent of time for a stationary state. You can have any questions in which you will ask, like you will be asked, uh, this is a stationary state wave function and what is the probability, and you may have the MCQs as all the all the options except one which is dependent on t. For the one which is independent of t, you can use that as an option. So for stationary states, the probability will be independent of time. So the probability density is independent of time t for stationary state, an important point to remember. So now we will also see the criteria for stationary states. What are the important points if the wave function is in a stationary state? The potential should be real and independent of time. Okay, real and independent, it's independent of time. I have just forgotten to write that. So the potential should be real. V of x should be real and it should be independent of time. Also the Hamiltonian should be independent of time. Probability density will be time independent. Independent, sorry, the probability density will be time independent. It's a mistake over there. And the individual states, now another important point where the individual states are stationary, like psi1 psi2 psi3 are stationary. Okay, I have a system and I say that the sub wave functions psi1 psi2 psi3 are stationary, which means they are independent of time. There is time is 0 over here. These are all sub wave functions. When they are mixed, when they are written in the main function and they are superimposed, that particular wave function will not be stationary. So you can see that if the individual states of are stationary, like all these psi1 psi2 psi3 are all stationary wave function, but when I superimpose them and write as a main wave function over here, then that particular wave function will not be stationary. But when we collapse it, and that particular wave function can be stationary, but the main wave function will never be stationary. So that much about the stationary state. Now let me say the next thing. You have an operator, and in classical mechanics you have x, p, everything. We directly just differentiate whatever we have in classical mechanics. But in quantum mechanics, if we have to differentiate an operator, what we have to do is take the expectation value of the operator and then differentiate it. Okay, so we have a formula for taking the differentiation of an operator. So the formula is as follows: d by dt of the expectation of A will be equal to commutators of A comma h and its expectation by IH cross plus partial differentiation of dou A by dou t and its expectation. So that much for today's video. So thank you, and remember all those formulas, write it down in your formula notebook, revise them daily. So see you in my next video. Thank you.